Today we'll talk about meta-reasoning. Meta-reasoning is thinking about thinking, knowledge about knowledge. In this case, the agent is not reasoning about something outside in the world. Instead, the agent is reasoning about itself, about its own knowledge, its own reasoning, its own learning. As an example, I can ask you, what is President Obama's telephone number? I'm sure all of you can immediately tell me, you don't know. But how do you know that you don't know? We touched a little bit about meta-reasoning when we were talking about learning by correcting mistakes. There we were interested in errors in the knowledge base. In journal, errors can also be in reasoning or in learning. We'll start today by talking about mistakes in reasoning and learning in addition to mistakes in knowledge. Then we'll talk about knowledge gaps, not just errors in the knowledge, but when some knowledge is actually missing. Then we'll talk about a very journal metacognitive skill which leads to strategy selection and integration. In this class, we have talked about a large number of methods, but we haven't yet talked about how an intelligent agent can put multiple methods together to address a complex problem. Then we'll discuss meta-meta reasoning or meta-meta-meta reasoning. How far can we go? Finally, we'll discuss an example of meta-reasoning in action that is sometimes called goal-based autonomy. We have come across the notion of meta-reasoning earlier in this class. You may recall this was the explanation that an agent had built to decide why a particular object was an instance of the cup. Then we told it that it was an incorrect decision. The agent then reflected on its knowledge. Here was the knowledge, here was the explanation it had built. It is now reflecting on it and trying to figure out what makes this particular explanation incorrect. Where does the fault lie? That was an example where the agent was reflecting on its knowledge. Perhaps this knowledge was stored in the short-term memory that had been pulled out of the long-term memory. But just like there can be an error in the knowledge, there could also potentially be an error in the reasoning or potentially an error in the learning process. An example of an error in reasoning occurred very early in this particular class. You may recall this particular diagram from mean sense analysis. This was the blocks microworld. The agent needed to take these blocks from this initial state to this goal state. However, there were multiple goals here, D on table, C on D, B on C. And as the agent tried to accomplish these goals, it ran into cul-de-sacs where no further progress was possible without undoing some of the earlier goals. So that was an example of metacognition over reasoning, where the agent was trying to figure out what was the error in my reasoning and how can I remedy it. We can similarly have metacognition over learning. So an example of metacognition over learning occurred when we were talking about learning by correcting mistakes. You may recall this was the explanation the agent had built after it had remedied the explanation. The remedy in this particular case was adding here that the handle is fixed and relating it to the rest of the explanation. Given that the agent had used explanation-based learning to build this explanation in the first place, we can think of the agent as reflecting on its process of explanation-based learning and asking itself, what did I do wrong? And then deciding, well, I built the wrong explanation. I must change that explanation, and that is what learning by correcting mistakes did. We can consider this to be a process of metacognition over learning in the sense that the agent may say, how did I learn this particular knowledge? Well, I learned it through explanation-based learning. So what was wrong in my process of explanation-based learning that led to this incorrect explanation? How do I fix my process of explanation-based learning so that I do not make the same error again? So far, we have talked about the case where there was an error in the knowledge, or an error in the reasoning, or in the learning. The knowledge, for example, was incorrect in some way. But the knowledge can also be incomplete. There can be a gap in knowledge, or in reasoning, or in learning. A gap in knowledge occurred when we were doing this exercise under explanation-based learning. In that particular case, the agent had built this part of the explanation, and it also had this part of the explanation. But it could not connect these two because there was no knowledge to connect that an object that has thick sides and that can limit heat transfer will protect against heat. Once the agent detects this as a knowledge gap, then it can set up a learning goal. The learning goal now is acquire some knowledge that will connect these two pieces of knowledge. Once the agent detects a knowledge gap, it can set up a learning goal. The learning goal now is to be able to connect these two pieces of explanation. Notice that we are seeing how agents can spawn goals. In this particular case, the agent is spawning a learning goal. You may recall that when we did this exercise in explanation-based learning, the agent went back to its memory and found a precedent, found a piece of knowledge that enabled it to connect these two parts of the explanation. And so this link was formed, and the agent was then able to complete this explanation. This is an example how the learning goal was satisfied using some piece of knowledge. In this case, the knowledge came from the memory, but the agent could have potentially also acquired the knowledge from the external world. For example, it may have gone to a teacher and said, I have a learning goal, help me with the knowledge that will satisfy that learning goal. This ability to spawn learning goals and then find ways of satisfying or achieving those learning goals, or any goal in general, is another aspect of metacognition. So this was an example of how metacognition helps resolve a gap in knowledge. Now let us see how it can help resolve gaps in reasoning or learning. To see how metacognition can help resolve reasoning gaps, let us return to this example of using mean-sense analysis in the block's micro-world. Once the agent reaches a cul-de-sac in the reasoning, the agent could form a reasoning goal and ask itself, how can I help resolve this cul-de-sac? It may then be reminded of the strategy of problem reduction, which reduces these goals into several independent goals, and then the agent may go about achieving each goal one at a time. Thus, in this example, the agent set up a new reasoning goal and then used that reasoning goal to pick a different strategy and thereby achieve that reasoning goal. Note also that this is one way in which we can integrate multiple strategies. We first used mean-sense analysis, ran into cul-de-sac, formed a new reasoning goal, used that reasoning goal to pull in a different strategy, problem reduction, and then go back to the original strategy, mean-sense analysis, for achieving each goal independently. In this architecture for a cognitive system, we have drawn these boxes as if metacognition was completely separate from deliberation, and deliberation was completely separate from reaction. In fact, there might be considerable overlap between metacognition and deliberation. Some processes in deliberation might be viewed as metacognitive processes. Some processes of metacognitive might be viewed as deliberative processes. To see why the lines between metacognition and deliberation are blurry, let us return to this example from explanation-based learning. When we talked about explanation-based learning, we did not talk about metacognition at all. We can view the agent as saying, well, I do not know how to build a connection between this part of the explanation and this part of the explanation. Therefore, I'll set up a reasoning goal which pulls at some other knowledge, and so on. Now that we know the vocabulary of metacognition, it is easy to view all of that in terms of this new vocabulary. So instead of thinking of deliberation and metacognition as two separate independent boxes, a better way might be to think in terms of boxes that partially overlap, as a meta space and as a deliberation space. We should not be overly concerned whether something should go into the deliberation space or into the metacognition space. The more important thing is, what is the content of knowledge that we need to carry out a process, and what is the process that we need to carry out? In this course, we have learned about a large number of reasoning methods. Here are some of them. We could have added a lot more here, for example, pattern refinement, or logic, or scripts. Typically, when you and I program an AI agent, we pick a method and we program that method into the agent. One unanswered question is, how might an agent know about all of these methods and then autonomously select the right method for a given problem? This is the problem of strategy selection, and metacognition helps with strategy selection. Given a problem, and given that all of these methods are available to the agent to potentially address the problem, metacognition may select between these methods using several criteria. First, each of these methods requires some knowledge of the world. For example, case-based reasoning requires knowledge of cases. Constraint propagation requires knowledge of constraints, and so on. Metacognition may select one particular method depending on what knowledge is exactly available for addressing that specific input problem. If for that specific input problem, cases are not available, then clearly the method of case-based reasoning cannot be used. If, on the other hand, constraints are available, then constraint propagation might be a useful method. Second, if the knowledge required by multiple methods is available, then metacognition must select between the competing methods. Another criteria for selecting between these methods might be computational efficiency. For a given class of problems, some of these methods might be computationally more efficient than other methods. As an example, if the problem is very close to a previously encountered case, then a case-based reasoning might be computationally a very good method to use. On the other hand, if the new problem is very different from a previously encountered case, then case-based reasoning may not be a computationally efficient method. We have come across this issue of computational efficiency earlier in the class. For example, when we were discussing generate and test, if the problem is simple, then it is potentially possible to write a generator that will produce good solutions to it. On the other hand, for a very complex problem, the process of generating good solutions may be computationally inefficient. Similarly, if there is a single goal, then the method of mean-sense analysis might be a good choice. On the other hand, if there are multiple goals that are interacting with each other, then mean-sense analysis can run into all kinds of cul-de-sacs and have poor computational efficiency. A third criteria that metacognition can use to select between these various methods is quality of solutions. Some methods come with guarantees of quality of solutions. For example, logic is a method that provides some guarantees of the correctness of solutions. Thus, if this is a problem for which computational efficiency is not important, but the quality of solutions is critical, we might want to use the method of logic because it provides some guarantees of the quality, although it might be computationally inefficient. The same kind of analysis holds for selecting between different learning methods. Once again, given a problem, the agent may have multiple learning methods for addressing that particular problem. What method should the learning agent choose? That depends partly on the nature of the problem. Some methods are applicable to that problem, and some methods may not be applicable to that problem. Second, for example, in this learning task, if the examples are coming one at a time, we might use incremental concept learning. On the other hand, if all the examples are given together, then we might use decision tree learning or identification tree learning. Another criteria for deciding between these methods could be computational efficiency. Yet another criteria could have to do with quality of solutions. Now that we have looked at strategy selection a little bit, let us look at strategy integration. Even if the agent selects a particular strategy, it is not necessarily stuck with that strategy. As the problem solving evolves, it may well decide to shift from one strategy to another strategy. As an example, consider that for a given problem, metacognition decides to select the strategy of case-based reasoning. Now, case-based reasoning spawns a number of subtasks: retrieval, adaptation, evaluation, and storage. Metacognition can now examine the requirements for each of the subtasks. And then, for each of the subtasks, it may decide on some strategy. For example, for the task of adaptation, metacognition may pick the method of case-based reasoning recursively, or it may pick the method of rules to adapt a case, or it may use models for the case adaptation. If metacognition picks the method of rule-based reasoning, then note the metacognition has shifted from the method of case-based reasoning overall to the method of rule-based reasoning for a subtask of case-based reasoning. We can also use a similar analysis at the next lower level. Suppose that metacognition decides to pick the method of rule-based reasoning for doing the case adaptation. Now the question becomes what rule to apply, rule 1, 2, or 3. We can imagine meta-rules that select which rule to apply under a given condition. We have come across the use of metacognition for strategy integration earlier. In this blocks microworld, we saw how mean-sense analysis can reach a cul-de-sac. When the cul-de-sac happens, metacognition may set up a new reasoning goal and select a strategy of problem reduction for resolving the cul-de-sac. When problem reduction then sets up 4 independent goals, we may revert back to mean-sense analysis to achieve each goal independently. In this particular case, we have integrated mean-sense analysis and problem reduction, and the reasoning has shifted between these two strategies in a seamless way. That's why we have talked about some of the uses of metacognition. We can use it to fix errors in knowledge or reasoning or learning. We can use it to fix gaps in knowledge, reasoning, or learning. We can use it for strategy integration. One thing that we have not yet talked about is what is the process that metacognition uses? What is its strategy? Well, metacognition can use the same kinds of reasoning processes that it itself is reasoning over. That is, case-based reasoning is a potential strategy for metacognition, constraint propagation is a potential strategy for metacognition, and so on. Let us take an example. Supposing that metacognition comes across a problem and it must select among these strategies. Metacognition might ask itself, what strategy did I pick the last time I came across a similar problem? This is case-based reasoning at a meta level. To complete this example, metacognition might say, the last time I used constraint propagation as a technique for this particular problem, this time I'll use constraint propagation again. As another example, given a second problem, metacognition may use planning to set up a plan for using these various strategies, thinking of each of these strategies as an operator.
As a third example, metacognition might get a new problem and decide to use every single method at its disposal to generate a possible solution. It then might have some heuristics to test each one of those possible solutions and figure out which one is best. So then it's using generate and test to select between its multiple strategies.
To summarize this part then, metacognition can use the same reasoning strategies that we have been studying at the deliberative level.
So if metacognition reasons over deliberation, could we also have an additional layer where meta-metacognition reasons over metacognition? And to take that even further, could we have a meta-meta-metacognition that reasons over meta-metacognition all the way up, infinitely up in a hierarchy? Is this a good way to think about the levels of metacognition? So personally, I would say no, this is not a good way to reason over it. We talked about in the previous portion of the lesson that metacognition uses the same strategies that it reasons over. It reasons over case-based reasoning, it reasons over means analysis, it reasons over problem reduction, but it also uses case-based reasoning, problem reduction, means analysis, and the others to do that reasoning. So it really doesn't need an additional layer. It's already equipped with the ability to reason over case-based reasoning and the other methods, so it can just reason over itself.
This is really cool. So AI agents don't need multiple levels of metacognition because metacognition can reason over itself recursively. In fact, current theories of metacognition all talk about this kind of two-layered system between deliberation and metacognition.
So meta-reasoning can be very difficult to talk about because it's circular, so it's often unclear what exactly we're talking about at a given time. So to try to make this process more explicit, let's take an example. Let's imagine a robot whose task is to assemble a camera, and all day every day the robot sits there assembling camera after camera. Then one day, the boss walks in and says, instead of assembling that camera, disassemble this camera that's already been put together. So what does the robot do? It wasn't programmed to disassemble cameras, so how does it figure out how to do this task? Well, the robot might have a rule that says, given a new goal or given a new problem, choose the method for which I have the most knowledge. The robot might then look at its memory and say, well, the only thing I have is a bunch of cases of assembling camera after camera after camera. So this is metacognition. The robot has now thought about what it knows, it's thought about its new goal, and it's decided on a method to use to approach this new problem. But now that the robot has selected a method, it then needs to reason further. It's chosen case-based reasoning as its reasoning method. But how will it do the adaptation? Well, the robot might then select a rule out of its memory that says, to reverse a process, do the steps in reverse. So now we've done not only strategy selection when we selected case-based reasoning, but we've done strategy integration. That it's now using a rule-based approach to take care of the case adaptation. So the robot uses that rule, reverses the steps, and disassembles the camera. Now the boss comes back by and says, well, yeah, you disassembled the camera, but why did it take so long? You could have done it so much faster. But the boss doesn't give any feedback as to how the robot could have done it faster. Then later, the boss brings back another camera and says, here, disassemble this camera, but do it faster this time. So now the robot needs to select a method again. It thinks, last time I used case-based reasoning to select my method for disassembling the camera. But case-based reasoning didn't give me an optimal solution. The boss complained that it took me too long. So instead, the robot chunks a rule that says, given a new task of disassembling a camera, suggest strategies other than case-based reasoning. So now it's used a form of meta-metacognition. It's thought about its metacognition. It's looked at the way it selected a strategy in the past and decided, the way I selected a strategy in the past must not have worked because the strategy I selected wasn't ideal. So next time, select a different strategy. So here we've seen everything we've talked about today in action. First, we saw using metacognition to resolve a gap. The agent didn't have any way of disassembling a camera, so it used it to select a strategy for resolving that gap. That's also strategy selection. It used case-based reasoning to decide what method it should use to resolve this gap. We then saw strategy integration, where it used a rule-based approach to adapt its prior cases. We then saw correcting mistakes, where the boss told the robot that it didn't do it fast enough, so its reasoning method must have been suboptimal, so next time it should try something different. That last part is also an example of meta-metacognition, or metacognition about metacognition. It looked at its strategy selection method and decided, next time I should select a strategy differently.
David's example of a robot that knows how to assemble cameras, but then is given the goal of disassembling a camera, is a good example of goal-based autonomy. Earlier, we had looked at how an agent can go about repairing its knowledge or reasoning or learning when it makes a mistake or reaches a failure. But sometimes it is not so much that the agent reaches a failure as much as it is that the agent is given a new goal. When the agent is given a new goal, we do not want the agent to just fall apart. We do not want brittle agents. We want agents that can then adapt their reasoning methods and their learning methods to try to achieve the new goal, even if they were not necessarily programmed to achieve that goal from the beginning. We know that human cognition is very robust and flexible. You and I address a very large number of tasks, a very large number of problems, and achieve a very large number of goals. If we are to design human-level, human-like AI agents, then those AI agents will have to be equally robust and flexible. Metacognition provides a powerful way of achieving that robustness and flexibility. It does so by flexibly, dynamically selecting among competing strategies. It does so by flexibly and dynamically integrating multiple strategies as the problem solving evolves. It does so by using reasoning strategies and knowledge that were programmed into it to achieve new goals.
So like we said earlier in this lesson, we've actually been talking about kinds of metacognition throughout this course, even if we didn't call it that at the time. we were talking about agents reflecting on their own knowledge and correcting it when they were introduced to a mistake. Earlier in this lesson, we also talked about the possibility that an agent would reflect on the learning process that led it to the incorrect knowledge and correct that learning process as well. Back during partial order planning, we talked about agents that could balance multiple plans and resolve conflicts between those plans. This could be seen as a form of metacognition as well. The agent plans out a plan for achieving one goal, a plan for achieving the other goal, and then thinks about its own plans for those two goals. Then it detects the conflict between those plans and resolves that conflict accordingly. Then it detects the conflict between those two plans and creates a new plan to avoid that conflict. Here, the agent is reasoning over its own planning process. We saw this in production systems as well. We had an agent that reached an impasse. It had two different pitches suggested and it couldn't decide between the two. That spawned a new learning goal, to find a rule to choose between those pitches. It then selected a learning strategy of chunking, went to its memory, found a case, and chunked a rule that would help it resolve that impasse. In this case, the agent used that impasse to set up a new learning goal. It then selected a strategy selection, to achieve that learning goal. We can also see metacognition in version spaces. Our agent has a notion of specific and general models, and it also has a notion of convergence. The agent is consistently thinking about its own specific and general model and looking for opportunities to converge them down into one model of the concept. And finally, we can very clearly see metacognition in our lesson on diagnosis. We talked about how the results of our treatment become new data for our iterative process of diagnosis. If our treatment didn't spawn desirable results, it also spawns data for the meta layer. Not only do we still want to diagnose the current malfunction, but we also want to diagnose why we weren't able to diagnose it correctly in the first place. So now we're diagnosing the problem with our diagnosis process. So as we can see, metacognition has actually been implicit in several of the topics we've talked about in this course. So finally, to make things as meta as possible, meta-reasoning has actually been a motivating pedagogical goal for the design of this very course. You'll notice that for almost every lesson, we've started with an example of a problem that you could solve. In incremental concept learning, for example, we started by giving you several examples of foos and not foos, and then we asked you, is this a foo? In production systems, we gave you some information about a baseball game and asked you to decide what the pitcher should do next. In learning by recording cases, we gave you a world of rectangles and asked you to decide what color a new rectangle might be. In classification, we gave you a bunch of pictures and asked you to decide which of those pictures were birds. In planning, we gave you our blocks microworld and asked you to develop a plan to go from our initial state to our goal state. In each of these, we've started with a problem that we could solve that we then wanted to design an agent to solve. These examples then motivated our discussion not necessarily of how we did it, but how we could design an agent to do it. Then at the end of each lesson, we revisited that example. We took the reasoning method that we designed for our agent and looked at how that exact reasoning method would allow it to answer the same example with which we started the lesson. When you did the example at the start of the lesson, you didn't necessarily know how you were able to solve that problem. You could speculate, but you never know for sure. But then by building an agent that can solve that problem, we start to gain some understanding for the processes that we must be able to engage in order to solve that problem as well. So by designing the agent, we develop a greater understanding of our own cognition. So in this way, the very design of the lessons in this course has been driven by trying to develop metacognition in you. In fact, developing metacognition in students is the entire goal of my own PhD dissertation. So how would you use meta-reasoning to design an agent that can answer Raven's progressive matrices? Throughout this course, we've covered a wide variety of different methods for addressing this test, and each method has its own strengths and its own weaknesses. Certain methods are better for some problems and other methods for other problems. Meta-reasoning would tell us, though, that you don't have to choose just one. Your agent can have multiple methods to choose from. Discuss how you might design an agent to have meta-reasoning. What methods would it have to choose from? How will it evaluate a new problem and decide what method is best for that problem? How much improvement do you really expect to see in your agent's performance based on equipping it with meta-reasoning? And finally, will your agent engage in any kind of meta-meta reasoning, as we've discussed? Will it not only think about the methods themselves, but also about how it's selecting a method? And if so, how will that improve it even further? So today we've talked about meta-reasoning. This very strongly leveraged and built on nearly everything we've talked about so far in this course. Meta-reasoning is, in many ways, reasoning about everything we've covered so far. We started off by recapping learning from correcting mistakes and the related notion of gaps. Then we covered two broad metacognitive techniques called strategy selection and strategy integration. We then discussed whether or not meta-meta reasoning might exist, and we decided ultimately that such a distinction isn't even necessary. After all, the structures involved in meta-reasoning, like cases and rules and models, are the same as those involved in reasoning itself. So meta-reasoning is already equipped to reason about itself. Finally, we discussed a particular example of meta-reasoning called goal-based autonomy. Meta-reasoning is in many ways the capstone of our course. It covers reasoning over all the topics we've covered so far, and it provides a way that they can be used in conjunction with one another. We do have a few more things to talk about though, and we'll cover those in our advanced topics lesson.
Meta-reasoning arguably is one of the most critical processes of human cognition. In fact, some recent research suggests that developing metacognitive skills at an early age in life may be the best predictor of a student's success later in life. Actually, this makes sense. Meta-reasoning is not about simply learning new information. It is about learning how to learn, about learning new reasoning strategies, about integrating new information into memory structures. Meta-reasoning is also connected to creativity. In meta-reasoning, the agent is monitoring its own reasoning. It is spawning goals. It is trying to achieve them. Sometimes it suspends a goal. Sometimes it abandons a goal. These are all part of the creative process. Creativity is not just about creating new products. It is also about creating the processes that lead to interesting products.
So you might notice that these quizzes at the end of every single lesson have asked you to talk about what you learned in this lesson, to reflect on what you learned in this lesson. One of the goals of these final quizzes is to facilitate your own metacognition about your learning of this material as well. So by answering this, you think about your own learning and hopefully improve it for the future. So, what did you learn during this lesson?
Thank you for answering this quiz on metacognition.